So the session is now being recorded so that you can refer to it in future if you need to. Please confirm that you're able to hear me and you're also able to see me clearly so that when we begin, I just start off without any issues. Are you able to hear me clearly? Are you able to hear and see? Juguna. Hana Wangui. Okay. So if you're able to hear and see clearly, then we can start. All right. So in the previous classes, then we were able to discuss, the PC interconnection structures. You can find that in the previous video. And we were also able to introduce chapter 2, which is input-output organization, where we say that here we're going to be dealing with how the computer system treats input and output, how computer system treats input and output, and the different technologies involved in the same. And therefore, we're able to introduce input-output modules. We said what a module is. We said a module is an interface between an input cable and the computer system. And we say that every port in the computer system has it has a module, and it's the module is the interface that does such functions as processor communication. In other words, transferring communication from the CPU to the device that has been connected, device communication, meaning that the computer is able to detect that device has been connected, control and timing, buffering. Buffering, we talked about things like printers and mouses and keyboards. We say that data buffering is basically temporarily storing instructions before execution happens if the RAM is preoccupied, and it eases and relieves the RAM from a lot of storage at a given time in a multi-processing environment. We also talked about error detection. It is the I/O modules that do what? That actually detect errors. For instance, if you plug in a flash disk that is faulty, it is that I/O module of the USB port, the interface, that will detect that particular error and communicate it. All right. So we talked about those. We also said that I/O modules are basically I/O interfaces. There is no difference. I/O modules are I/O interfaces. And where we reached is where we were now were to begin discussing the modes of transfer. How data bits or binary information is transferred from an input device to the CPU, or from the CPU to the input device to an output device. So modes of transfer. So we said that there are three different ways in which data or instruction bits can be transferred from the CPU and between the CPU and input-output devices. Like for instance, if you click open using your mouse, if you click delete, if you click rename, if you click move, or you type something on the keyboard, how is that information all able to go to the CPU for execution? All that. Or how is information that comes from the CPU able to go to the monitor for your viewing, or to the speaker for your hearing, or to the printer for printing? Such things. How is data bits, binary information, moved around in the computer system? So there are three modes of data transfer between the I/O devices. We were able to introduce them. One of them is programmed input output, or programmed I/O. The other is interrupt driven IO. We normally call it interrupt initiated or interrupt. So that we can now see what we are having. Let's begin with programmed IO. Programmed IO, this works as a result of IO instructions written in the computer program. Each data item transfer is initiated by an instruction in the program. It usually the transfer is from a CPU register in memory. Of the peripheral devices. An example of programmed IO is in this case, IO device does not have direct access to the memory unit. A transfer from IO device to memory requires the execution of several instructions by the CPU, including an input instruction, the data from device to the CPU, and store instruction to transfer the data from CPU to memory. In programmed IO, the CPU stays in the program loop until the IO unit indicates that it is ready for data transfer. This is a time-consuming process since it needlessly keeps the CPU busy. It needlessly keeps the CPU busy. Just a minute. Just a minute. I think my screen sharing has ended.
You are currently the only person in this conference.
Sorry for that. Sorry for that. So let's continue. Programmed IO. So basically, I was reading for you how the programmed IO works, and programmed IO is basically the mode of data transfer, which is one way. One way. One way. Why? Because it is only the CPU that is allowed to communicate to the devices, but the devices don't communicate back to the CPU. That's called programmed IO, and it normally works for critical services. Critical services in the computer. Now there are those that are systems. There are those that are recognized as system services, and there are those that are user services. Normally, if you open the task manager, you are actually able to see some of the services that are some of the services that are user-based services, and the other services that are system-based services. Now there are system-based services. System-based services are basically services that do not need user intervention. Services that do not need user intervention. For instance, RAM management, CPU, processor scheduling, those kinds of services that really do not require user intervention. They are system services, and therefore for those kinds of services to happen, of course they need signals to instruct them, right, from the CPU, because it is the CPU that controls all those activities, right? So they need signals, they need some form of communication. So these programmed input output are to facilitate those kinds of services, Also, there are those services like what we call the plug and play services, where when you mount a keyboard to a desktop. It just has to pick it. All right. You don't have to, configure. You you don't have to configure. The CPU can directly communicate to that device that you have connected. So plug and play services are also they are also accommodated in what we call the programmed I/O. All right. So basically, that was what programmed I/O works. It works with what we call the essential system services that need no minimal or no user intervention. Programmed I/O, as I've said, that normally programmed I/O works one way from the CPU to the devices, and not the devices to the CPU. Okay, from the CPU to the devices, like plug and play. If you connect a mouse to your device, the CPU communicates to the mouse directly at that point when you connect or when you plug in, right? So that is what we call programmed I/O. Now, also the other feature of programmed I/O, the reason it's called programmed I/O is because they are already built to happen. They are already built to happen. The instructions that are already pre-built, they're already predefined. Those signals will at the time they are set to to be sent from the CPU, they are going to be sent. That's why they are called programmed I/O. Okay. Then go to interrupt initiated or interrupt driven I/O. Now, the first thing to understand before we even discuss the interrupt driven I/O is to know what an interrupt is, right? To know what an interrupt is. An interrupt is basically an activity that is considered high priority during a lesser priority activity. Okay, an interrupt is an activity that is considered high priority during lesser priority activity. All right, so that's what an interrupt is. It's an activity in the computer system that is considered or deemed by the CPU as a high priority activity when it is initiated. So when that activity occurs, all other activities that have been happening at the same time are considered low priority for this particular activity. They are called interrupts. All right, they are called interrupts. For instance, there are those system notifications that come up so that you can be able to do some things without which your computer may not continue to do anything else. All right, so those are called interrupts, and they are considered high priority, and they are given system time, they are given CPU time, and they are also given priority in memory allocation. So basically, interrupt driven I/O. These are input output signals that come from interrupt services. Okay, that come from interrupt services. By using interrupt facility and special commands to inform the interface to issue an interrupt request signal whenever data is available from any device. The interface, meanwhile, keeps monitoring the device. Whenever it is determined that the device is ready for data transfer, it initiates an interrupt request signal to the computer. Upon detection of an external interrupt signal, normally the CPU stops momentarily the task that it was already performing and branches to the service program, all right, to process that interrupt and then return to the task it was originally performing. So that's why I've told you it's basically an input-output signal that is considered high priority. For instance, for instance, you could be connected. Your computer could be connected to a printer, and as you are printing, there will be a message from the printer that the probably the ink is over, or the toner is is faulty, something you need to repair so that printing can continue. All right, now that is not an error message. That is not an error message. That is just an interrupt message. Are we together? That is an interrupt message. I think you've ever experienced such things. You're doing, something, and then you receive a notification, and you cannot continue to do what you have been doing unless you solve what that notification says. So if it's a printer, it can be a toner. You'll see them a message that your toner is faulty, or your ink is drained out. So you will have to do that first. In other words, you cannot do anything else, and a related activity if that particular interrupt is not addressed. Okay, so that particular signal that has come from the printer to the computer, and the CPU initiates, the CPU, interprets that instruction, and is able to be displayed on the monitor for you to view it. That particular signal that has come from the printer about the tone or the ink that you need to address is called an interrupt message. Okay, so an interrupt is a high priority activity from an input or output device, which needs to be addressed at the time when other activities are being performed, such that when that interrupt occurs, other activities that have been occurring at the same time will be by default considered low priority. All right, and they will be given, therefore low priority activities are normally assigned lesser memory, they are normally assigned lesser CPU time, and yeah, and they may even be jolted out of the CPU time so that they can be rescheduled, okay, because they are considered less priority. All right, so those are interrupts. So that is what interrupt IO is. Interrupt driven IO is. This is a mode of data transfer that allows interrupt services to communicate with the CPU. Okay, all right, then direct memory access. The DMA, the data transfer between a fast storage media such as a magnetic disk and a memory unit is limited by the speed of the CPU. Thus, we can allow the peripherals directly communicate with each other using the memory buses, removing the intervention of the CPU. This type of data transfer technique is known as DMA, or direct memory access. During DMA, the CPU is idle and it has no control over the memory buses. The DMA controller takes over the buses to manage the transfer directly between the I/O devices and the memory unit. Now, DMA normally works with high-speed storage media, like magnetic disks and optical disks and such things. When you plug in a flash disk, it is not always necessary that the information from the flash disk is going to be directly controlled by the CPU, because itself it has a module. The USB itself has a what? It has a module. That particular USB port where you plug in your device, the USB device, it has a what? It has a USB module. It has a USB interface. So it is the USB interface that does what? That provides direct memory access. It provides direct memory access. Therefore, you are able to, it also allows us to do things like copying and pasting, moving files from one disk to another without the CPU being too much involved, meaning that the CPU is going to be idle, or if busy with other activities, other computing activities. So if you connect, for instance, a USB, and you want to do some copying to a machine, or from the machine to the device you have connected, it is this direct memory access that comes in play. All right, direct memory access, it comes in play so that the CPU may not be engaged, in your transfer and whatnot. Uh, so that is basically that is what direct memory access is. Now, because direct memory access does not need a high intervention of the CPU like other processing activities, there will be two things that will happen for direct memory access to successfully occur. There are two things. One is called bus request, and another is called bus grant. Bus request and bus grant. Basically, bus request is used by the DMA controller. DMA controller is basically a code in the what? In the IO module. Okay, so it's not a what? It's not a device. Okay, it's a code, it's a functionality. Uh, the DMA controller requests the CPU to relinquish the control of the buses. All right. And then bus grant, it is activated by the CPU to inform the external DMA controller that the buses are in high impedance state, and the requesting DMA can take control of the buses. Once the DMA has taken the control of the buses, it transfers the data. This transfer can take place in many ways. Now, why are we dealing with buses? Remember when we were discussing the von Neumann architecture, we discussed that buses are a primary part of the computer system, and they are a primary component to facilitate communication in the computer. They are pathways for data transfer. And one of them we looked at was what? Well, we called it the data bus, right? We had three kinds of buses: data bus, address bus, and control bus. So it is the data bus that allows data to be transferred when you are copying files to the flash disk, or from the flash disk to the hard disk and whatnot. It is a data bus that facilitates those things to occur, those kind of activities to occur. So that's why we are dealing so much with bus request, buses. That's why we have bus request and bus grant. In other words, bus request is where the DMA controller requests the CPU to relinquish the control of one of the buses, and one of those buses, which one? The data buses. Okay, so that there are some data buses at that moment when you want to transfer, like a file from your flash disk to the computer, to the hard disk of the computer. One of the databases is going to have to be relinquished, or to be given over, so that it can be used for what? To facilitate the copying or the moving. Are we together? So that's why we have the bus request. Okay, one of the buses has to be requested. One of the buses has to be requested. Then bus grant is when a bus has been given or granted, so that now communication can happen from basically a flash disk to a hard disk, or a hard disk to a flash disk, etc. So this is how the DMA works. First a bus is requested, then when bus is granted, then direct memory access occurs. Okay, you're able to copy, cut, move, such kind of things. All right, so I'm not going to go into types of DMA. You're going to read those, the types of DMA, as long I've already given you the concept of how DMA works. So you're going to look at that, the types of DMA. Then let's look at IO processor. Now I want us to see how these things are moving and flowing with each other. We began with what? IO modules, okay, and then we went to IO transfer. Now we are at IO processor. So I want you to really notice how they flow and how they relate to one another, so that at the end of the day, you may not find yourself not really knowing how they relate to one another, because it is in knowing how they relate to one another that you can appreciate generally the unit itself. Okay, so we move from IO modules, where we said that input output devices need a what? An interface. All right. Then we went to IO transfer, where we looked at how input and output devices transmit signals to and from the CPU, right? Where we looked at the three kinds of transfer methodologies or modes. Then now we are at IO processor. So what is this about? Now, an IO processor, normally we just call the IOP. It is a processor with direct memory access capability. A processor, IO processor, is a processor with direct memory access capability. Direct memory access capability. Now, I want you to understand that this is not the normal CPU chip. This is not the chip of the computer itself. This is not the system chip, the CPU chip itself. All right. This is an IOP. all right? A processor basically and mainly for an input device or an output device, a particular processor for that particular input device. Yeah, so it's not the main processor chip inside the the system unit. So basically, this is a processor with direct memory access capability. Okay, that's why we are saying here, as you can see in this statement, it is a specialized processor which loads. I hope you've seen this very key term. It's a specialized processor, meaning it's not the chip itself, the one that is normally in the system unit, mounted on the motherboard. This is a specialized processor which loads and stores data into memory along with the execution of I/O instructions. What is its function? It acts as an interface between system and devices. It involves a sequence of events to executing I/O operations and then store the results into the memory. Each input output processor controls and manages the input output tasks. The IOP is similar to the CPU, the main one, all right? CPU, similar to the main CPU, except that it handles only the details of what? IO processing. The IOP can fetch and execute its own instructions, and these IOP instructions are designed to manage IO transfers only. Well, let me summarize what those statements mean. The reason I read for you is so that you can capture basically the essence of that particular item, so that when I discuss it, you can relate to what we just read. So basically, the IOP is a specialized processor. These are specialized processor uh, chips for input output devices. Now, we always in the implementation of computer devices or interactive computer devices, we have to integrate what we call IC chips, integrated circuits. All right. So integrated circuits are basically they were first to be used, in which I think you've already done introduction to computers, introduction to ICT, evolution of computers. I think you are able to do the 5 generations of computers, and you are able to say that there were 5 generations, and IC integrated circuits were first introduced in which generation? In the third generation. So in the third generation of computers, ICs were introduced, and we have always used ICs since then. Okay, it's only that they have been more modified and made better. As you can remember, in uh, in uh, in third generation computers, you actually they came up with ICs. It's for processing. All right, so that was a transition from what? Transistors, right? Transistors were being used for processing in the second generation computers, and before that there were what? Vacuum tubes, right? So as they moved along, they came up with ICs, integrated circuits for processing. Then in the fourth generation, they used large scale ICs, large scale integrated circuits. You realize these are just ICs that are being modified and made better, okay, in order to support more devices, more instructions per second, those kinds of things. And then in the fifth generation, where we use what we call very large scale VLSICs, very large scale integrated circuits. Okay, but again, they are circuits, they are integrated circuits. They have never changed. They are just integrated circuits that have been made better and better, um, given the power to handle more instructions, to handle more complex multiprocessing environments, and such kind of things. Okay, so ICs have always been in use. So normally, most input devices, especially those that come separately, most input devices that come separately, and output devices and that come separately, they have their own what? They have their own ICs. They have their own chips for processing. Consider a machine like a printer. All right. consider a machine, and we are not talking about the mechanical printers like the daisy wheel and the dot matrix. We are talking about the the thermal, the inkjet printers, the laser printers, those printers that can be considered to be by nature and by extension computer devices, all right, because they can actually accept hard flash disks, they can accept those devices, right? So they can actually be considered to be what? Computer devices by extension, only with specialized what? Active functions. So those kinds of devices normally come with their own what? Their own processor. All right, with their own processor. I want you to imagine a printer that can support, you can plug in flash disk, it can support network transfer. There are printers that support Bluetooth. Okay, there are printers that support Bluetooth, such things. There are, and among all that, they are able to print, they're able to scan, they're able to do all those activities. What manages them? It's a processor, all right? Because remember, the function of a CPU, whether it is an IOP or a normal CPU, the basic function of any processor is to basically do what? Convert instructions to meaningful information that can be executed, right? Or to interpret instructions and to execute them, right? So if a machine really has a lot of executions to happen, it needs a what? It needs a processor. So there are input and output devices that come with their own specialized processors because of the nature of activities they do. So I've given you an example of a printer, a thermal printer or a laser printer that supports Bluetooth networking. It supports you can plug in storage devices. You can print from a USB. So all those activities, yet it's just a printer. They have to be coordinated by what? A CPU. Therefore, that CPU of that particular device is called a what? An IOP. All right, an input output processor. So basically, input output processors are processors for input output devices that have a lot of instructions to be executed. A lot of instructions to be executed. Consider also a POS system. All right, a POS, point of sale, a point of sale system. In a point of sale terminal, I believe you know what that is. When you go to the supermarket, you buy your products, you go to the cashier at the front of the supermarket, and you pass your products there. They are passed through a barcode reader, which is able to read the price of the product and all that. Now that all of that, there is normally in some, you will find out what? There is actually a printer to print receipts, a specialized printer to print those kinds of receipts of that nature. Now those kinds of printers, they are not just mechanical in nature, they are also electronic. All right, they are not mechanical, they are also electronic. So that kind of a device, because it's an output device, it needs a what? A process of its own, all right, so that it can execute and interpret instructions. Interpret and execute, of course, it happens in that order. It first interprets, then it executes, and interpret and execute instructions. All right, so that kind of a device will need a process of itself. So that kind of a processor will be called a what? An IOP, an input output processor, an IOP. So why do we need IOPs? We normally need IOPs so that we can relieve the main CPU of the task that those devices do. Can you imagine of a printer which does a lot of activities, like it can support Bluetooth transfer of data or documents, it can support network transfer, Ethernet transfer. It also supports you are able to print your documents from your flash disk directly. Can you imagine if that printer depended on the CPU of a machine? Now, we'll need actually a machine that really has a lot of CPU power and capability to support other activities of the computer itself and to still support this particular printer. Can you notice that? So that is why we need IOPs. IOPs are basically so that we can relieve the CPU of the main CPU of the computer from a lot of tasks, so that these particular devices can have their own CPU to do their own tasks. They don't depend on the CPU of the connected machine or the connected desktop or laptop or computing device. Are we together? That's why we need IOPs. Okay. Moving on, we need to understand how an IOP works. So that's why we are here having a block diagram of IO processor. How the IOPs work. Now, this block diagram is basically to help you understand how IOPs work in relation to the computer memory and also the main CPU, the CPU of the computer itself. All right. So as you can see, we have a memory unit here. Memory unit is just something like a RAM. It can be a cache, just one of the primary memories. Okay. So memory unit, and then we have the CPU, the device, the CPU for the machine, and then we have an IOP, and then different peripheral devices can be connected to an IOP, or one peripheral device can have its own IOP, like in the example that I've given you for specialized printers. Okay, it can have its own IOP, but different different peripheral devices can be connected to one IOP, and then that one IOP is now connected to the computer itself. Can you see how that works? So we can have peripheral devices, again, as we said in the previous classes, are devices that are connected to the computer externally. They are not inside the system unit, right? They are not mounted on the motherboard. They are connected externally, peripheral devices. So we talk about things like the keyboard itself, we talk about the mouse, we talk about printers, all these, even a monitor, even if you connect a separate screen, yeah, a separate screen, or even uh, you know, a thing for your gaming, those things that you connect for your gaming to the computer, those will be considered peripheral devices because they are connected to the computer system externally. Okay, so you can have, actually, if you have these peripheral devices that are having a lot of work to them, or a lot of instructions, bits per second, they have a lot of instructions to execute, then you can connect all these peripheral devices. Instead of connecting them each to the computer, you connect them, all of them, to an IOP, one IOP, and then it is that one IOP that manages all of them, and you connect that IOP to the computer itself through one of the ports. It can be a USB port, it can be a serial port. All right. So let me get you an image. That can help you understand what we are having. That can help you understand IOPs better. So let me get you an image. Okay, let me share. I hope you can see what you're having. All right, there we go. So these are kind of input output processors, and they are used in different application scenarios. For instance, we have input output processors for studios, for that are used with public address systems. Like this is one. Yeah, these are speaker processors. You see, a speaker is an output device. A speaker is an output device. So these are speaker processor. I think for you who probably have worked in studios or in sound teams of organizations like churches and such things, you've seen this kind of device. Normally, it's a processor for speakers, right? uh, it's an input output processor. Okay. Uh, can you see this one too? Have you ever seen anything like this? Yeah. Basically, it is just a digital processor. Okay. For speaker, a digital speaker processor. It's an input output processor. I think you've ever seen this. Is an input output processor. Okay. So it acts as an interface. It's a module and it's also a processor. Why? Most of the time when you lift this thing is normally heavy. It's not a light thing. Like for this one here, this is basically to receive input from mics, right? I think you've ever seen this. To receive input from mics. Let me scroll. Let me maximize. So this is to receive input from mics, and a mic is a what? A mic is an input device, right? It's an input device, and the sound goes probably to a recorder, right? Yeah. So this is a what? It's a processor. Why do we call it a processor? Because if you open in it, you'll find IC chips. Okay, you'll find IC chips. Yeah. So basically, these are input output process. Let me have another. This is an input output processor. Can you see how many chips can you see how it has many chips? It has a lot of chips. If you can actually notice, it has a lot of chips. These black things that you can see, these are what we call integrated circuits. Okay, these are integrated circuits. Okay, as you can see, this is not a motherboard, right? A motherboard normally has different things, but this one is just filled up with what? ICs. Okay, meaning that it's a what? It's a processor itself. It's like one big processor. Okay, it has a lot of ICs. So these are what? These are it's a what? It's an input output processor, and this is, I guess, when you can I'm trying to look at these red edges here where there are ports to connect some certain devices, and I want to believe that these are ports for voice over IP phones or something else, which I'm not sure. But basically, of course, these are ports to connect some certain input devices. All right. As you can see here, sorry, there is also a what? A processor for what? To use with a TV. For instance, if you are joining four TVs to work as one TV. I think you've ever seen this in some hotels. They join different TVs, especially in these hotels where people go to watch matches, as they have a good time with their friends. They normally connect these kind of, yeah, I think you've ever seen it, right? Even in malls, they normally connect different computers to work like one computer. Now, for you to be able to implement this, you need a what? A processor, all right? And this is an output processor, all right? Where now you connect all of these, all of these screens to HDMI ports, all right, to HDMI ports, and therefore they are able to be synchronized. So it is this device that synchronizes the images from all of the four computers. Let's say if there are four computers, this output processor, it synchronizes the images from all of them and makes them to appear as though they are one. Okay, so I think when we are discussing this, what you know in real life comes out more alive, right? This is an input output processor. Also, can you see it has a number of chips inside the black things? Those are IC chips. So basically, as we are discussing this, I think you are able to know what we are discussing so that it doesn't look like something is so far from you. These are things you know. This is an input output processor for what? synchronization of speakers, especially if you've ever worked or know people work in studios. They are able to manage the sound that goes to every speaker. So these are the ones that process sound. Why? Because sound is an output, right? Sound is an output. Also, it can be an input, of course, but in this case, it's an output going to the speaker. So these are processors to process that sound before it goes to the speakers itself, right? So I think you can now relate what we are talking about, right? You can actually relate to those are basically you can relate what we are talking about. So those are called the input-output processors that are normally connected to, that are normally used to connect input-output devices to the main computer itself. All right, to the main computer itself. So, for instance, if you want to open a studio, there are some certain devices that you cannot connect directly to the computer because there are no the right ports to connect those devices to. So you'll need a separate processor to connect those particular devices. Then you connect now that processor to the computer. All right. So if you want to control those kinds of devices, particularly in studios and such things, you want to control some kind of speakers that are of some kind of a unique kind of structure, or there is a recording machine that you want to connect to the computer so that you can control it using a software. Those kinds of things, you may not be able to connect them directly to the computer. All right. Why? Because of what? Because of the instructions per second that they have to generate or they have to work with. So your computer cannot do all that task. So you need a separate input output processor, particularly for that particular device. Okay. So they are called input output processors because they help people to manage input output devices without directly connecting them to the main CPU. Otherwise, the main CPU is going to be overwhelmed. All right. Okay. Okay, you can see that. So here we can have a peripheral device like a speaker, and then we have an IOP, one IOP for all those speakers, like the ones I've shown you in the images. And then now you can connect that IOP to the computer itself, right? To the computer itself. Yeah. Or you have a TV screen, and then you connect them to a processing device that can synchronize all those images so that they appear to be one screen, though they are 4 screens or 3 screens you've connected, right? So those are IOP. Yeah. Now let's go now to data communication processor. Data communication processor. Or is there any question before we move on to data communication processor? Any question? Any question before we move on to data communication processors? Can I give you a 5-minute break so that you absorb what we've already learned? I'll give you a 5-minute break. Do you need it or we continue? Odette, Coach, Catherine, do you need a Nikki, Chesire, Luke, Lace? Do you need a 5-minute break so that we can continue? Okay. Then we'll have a 5-minute break. We'll resume at 12:10. Oh, sorry, I was not recording. Sorry. So as I was saying, the data communication processors are used in to collect data that are connected in numerous remote terminals. It can be VoIP phones, phones that use the internet, that use Ethernet cables for communication, um, and other devices that need to be connected to each other, that need to be synchronized to work as one. Okay, so you connect all these IOPs together to a data communication processor. So this data communication processor is then able to synchronize all the communication that happens through all those IOPs. And then it is now this DCP that you connect it to a server, okay, to the server, so that all information can be recorded, all the calls that were made, all the calls that were received, all the mails that were sent to the computers, all the mails that were received by the computers, and such kind of things. All right, and such kind of things. So basically, the function of the DCP, the data communication processor, is to function as an IOP in a distributed environment. A distributed environment is one which has that has different services, different devices that are located in different places, and those devices are used as terminals. Okay, it's like think about an ATM machine. There are ATM machines all over the place. So there are ATM machines in geographical place A, ATM machines in the other town, ATM machines in the other town, ATM machines in the other town, but they all work as one. So that is what we call a distributed environment. So here we are not talking about ATMs, we're just talking about simple devices like VoIP phones. We're talking about screens, yeah, screens, right? Screens that you need them to work as one, right? Like they are displaying the same things. Can you think about what uh, think about in an auditorium, in a big auditorium that needs screens. Now all these screens have to be done what? They have to be connected to work as one, so that they display the same images, right? They display the same images. So if these are big high-end screens, if they are big high-end screens for these, normally these large auditoriums or even stadiums where people watch football or rugby or other matches or tennis or other matches, they have to have different screens stationed in different places. Now how are those screens able to function as one to display the same images in synchrony? Okay, so that they are all doing it in synchrony meaning they are doing it together without hitches, such that there are no you can't see, there is no difference between what you are seeing in this screen A and screen B. You can see the same things at the same time. Okay, so the way they do that is connect all these screens to what? A data communication processor for those screens. Okay, and why are we calling that a distributed environment? Because these screens are basically in different places. All right, they are not joined together as we had seen in the other previous example. They are not joined together to work like one screen, but they are different screens, each of them displaying the same images in screen A, same images in screen B. So I believe you understand what I'm talking about. So for those kind of environments where it's a distributed environment where different devices have to be interconnected and synchronized to work as one without overwhelming the CPU of the main computer that is being used, then we use a data communication processor. So basically the difference between a data communication processor and an input-output processor is that data communication processors are used especially for distributed environments. Okay, so it's where there are remote terminals, telephones, communication lines, computers, things like printers, display devices like LCD screens, digital sensors, and every other thing for the purpose of serving many users at once. So meaning that all those users are seeing the same, they are seeing the same thing. For instance, there are also the government can also be able to install screens on there or in town so that they can display what the government. For instance, if you ever watch movies and such things, you normally see that in some towns, there are screens. All right, they are not display screens for adverts. They are not display screens for adverts, but they're display screens specifically that are controlled by the government, so that they can, if there is any public communication they need to pass, people passing through the town can actually see without having to be somewhere watching TV, right? So and if all of these screens are stationed, one in this town, one in the other town, one in the other, and at the same time, if the government has something they need to go public with, they will all of those screens will display the same things at the same time without any hitches at the same time. So all those screens have to be controlled by what? By a data communication processor. Why? Because they are in a distributed environment. They are working like terminals. Okay, they're in a distributed environment. So that is what data communication processors are all about. What is a modem? Even without without that information, can somebody tell us what a modem is? What is a modem? What is a modem? Somebody? Catherine? Dennis? Dan? Don? Hannah? Kipngeno Lewis? Nikki Chesire? What is a modem? Olo? Wanyiri? What is a modem? A modem is it's like a joining together of two words: modulator, demodulator. You've done something about computer networks in Introduction to ICT, computer networking, and you touched on several devices that are used in wireless networking: routers, switches, hubs, bridges, gateways, modems, codecs. So a modem is basically a joining together of two words. It's a modulator, demodulator. The work of a modem is basically to convert signals, digital signals, to analog and analog to digital for the purpose of internet access when we are using different devices that use different kinds of signals. For instance, when you are using your computer, from transmission from a computer to a telephone line, you need to that signal needs to be converted from digital to analog, because your computer is a digital device, so it uses digital signals. Digital signals are signals that are discrete in nature, that only exist in the forms of 0 and 1, binary data, right? So for that signal to be converted so that information can pass through a telephone line, then it has to be modulated. Okay, it has to be modulated. So modulation is converting a digital to an analog signal. Then the recipient of that message that you've sent from your computer to a telephone line, then from a telephone line to the recipient computer, he also has to do what? That signal has to be reconverted from analog to digital, so that the computer can actually display or view. You can see it, you can open your email and see it, right? So demodulation is a conversion of analog signals to digital signals. So what does all that is a modem. So the work of a modem is normally used for, of course, generally people would say, a modem is for internet access, but for you, because now you are the one doing ICT, you need to know that what the function is, right? The function is to basically modulate and demodulate, convert digital signals to analog for transmission in telephone lines, okay, and analog signals to digital for transmission into digital devices or digital frameworks. That is what the work of a modem is. Now, modems, you can buy a modem from an internet service provider. You can buy a modem. in from local vendors, but most devices come with their own way of converting digital to analog and analog to digital. So you'll find that if you install a router, you will not need a modem. Okay, if you install a router, for like Wi-Fi access, you won't need a modem, right? Why? Because it already does what a modem does. Okay, yeah, and it even supports for wide area network, right? Or a metropolitan area network, a small geographical unit. So basically, a modem, that's its work. But why are we discussing it in under input output devices? Um, because every time you are receiving, every time you are receiving signals, you are sending an email, receiving an email, and all that. When you are doing that, you are dealing with input and output, right? Yeah. So that's why we are discussing it under input and output organization. But of course, mainly the modem is more well discussed in computer networking. Okay, so that is the function of a modem. So as you can see in this statement, modems convert digital into audio to be transmitted over telephone lines, just as I had said. So now let's discuss modes of transmission. Modes of transmission. How is data transmitted from sender to receiver and back, right? If you're using a modem or any other device for internet access, how does transmission happen? Now there are three modes of transmission. Transmission can either happen as simplex, half duplex, or full duplex. Right now, this is basically a repeat of networking, which you did in Introduction to Computers, but you can actually repeat so that we can just because we have time anyway, so that we can just see what they are. You already know them. So there are three modes of transmission: simplex, half duplex, and full duplex. Now, what is simplex transmission? A simplex transmission is where it is unidirectional. Simplex transmission is unidirectional. Unidirectional just means that at a given time, that simplex line can only support one signal, or one signal going through one direction only. Okay, so the receiver cannot communicate with the sender at the time that the sender is sending a signal. Okay, so simplex transmission, normally this is very, very applicable in walkie-talkies, the over-overs for policemen, right? Where you speak and then they speak, you speak, so you can't speak simultaneously, you have to alternate speaking. That is simplex transmission. Simplex transmission, or also in a plane, or in a train, when the captain or the pilot is saying things to the passengers. So that kind of a transmission is a simplex transmission, unidirectional. Okay, unidirectional, only one direction, or in a ship, those kinds of things. Yeah. Also in radio and television broadcasting, how the signals that you get, that your radio receives and your television receives, your radio and your television do not send signals back to the broadcasting satellite. They do not. Those signals are one way, they are unidirectional. Yeah, I think that makes sense. So radio and television broadcasting also apply the simplex transmission, mode. It is only one way. So when transmission happens one way, that is simplex transmission, unidirectional. Your television receives signals for different channels, but your TV does not transmit signals to the broadcasters. Your TV is just a recipient, right? So it just receives signals from the sending broadcasting satellite. Yeah, that is simplex transmission. Okay. Uh, please forget about the walkie-talkies and such. That one we're going to discuss it here. Half duplex. In half duplex system, it is capable of transmitting in both, but data can be transmitted in one direction only at a time. So here now we have walkie-talkies. So as you saw simplex, we gave examples like like the transmission medium that the pilot or the captain of the train or the captain of the ship uses to communicate with passengers, right? It is one way. You can't communicate back, just one way. Also for radio and television broadcasting, one way. The radio and the TV receive signals, they do not send back. Their work is just to receive from the broadcasting satellites. But half duplex is where it can support both ways, but one way at a time. Both ways, but one way at a time. So that now here we can now have the example of walkie talkies. So you can't talk unless they have finished talking, or unless they terminate that, they disengage that transmission line so that it can be free for you to talk back, right? That's why you find that for walkie talkies you have to talk, then say over and release that transmission line. You have to press and release that, or you have to release that button you are holding. You can't talk if you are not holding that button, because it is by holding that button that you kind of engage that transmission line for your talking. When you release it, the transmission line is now free for the other person to use it. So they press it at their end to engage it, and then they can talk back to you. I think you can understand how that works. So it's called half duplex. It happens in both directions. So simplex is unidirectional, half duplex is bi-directional. Okay, it is bi-directional, but the transmission line can only be used by one user, or by one signal going to one direction at one time. Then full duplex is a fully bidirectional transmission, where both sender and receiver can actually communicate at the same time. And that's now where we have things like uh, SIM subscriber calls. When you call someone using your SIM card, uh, telecommunication calls and such things, you're able to call and we talk, and we can actually talk at the same time, right? We can actually talk at the same time. We don't need the transmission is open. As long as I've called you and you've received, now the transmission is open for both of our frequencies to go through, both of our signals to go through at the same time. So we can talk, I talk back, I talk back, and we can even talk at the same time, and it still allows for that, right? And also for other examples like video calling, right? Video calling. So that was audio calling. Now we have video calling, yeah, or even video conferencing. You are able to meet other people via channels like Zoom, uh, Sorry for that. I experienced some challenge on my side, but I'm back now. Observe these diagrams and observe how they demonstrate how these transmissions work. So in Simplex, there is only one arrow that is pointing to the receiver, meaning that communication comes from sender to receiver only. That is the only way transmission works. Then half duplex, sender can send and receiver can also send, but at their own separate time. That's why we have two arrows, one to receiver and another from receiver to sender, half duplex. Then for full duplex, it's one line that can support both. So there is back and forth. That is why we have one arrow that points in twin directions. Okay, back and forth communication. All right. Now let us talk about protocols, communication protocols. Let's talk about communication protocols. We're just going to introduce and then I'm going to end it somewhere, right? So communication protocols. Now a protocol is basically a rule that governs something. So when we talk about communication protocols, these are basically rules, standards that govern how communication happens between senders and receivers in a network, right? So that is what a protocol is. It's a rule, it's a standard that governs how communication occurs. Okay, so when we are talking about protocols, we are talking about standards or rules for communication. Now protocols are normally there so that we do not likely have hitches when there is communication happening, so that there are standards that govern such that there are no hitches, there's no confusion. The devices that are in communication are recognized, right? The signals that are being sent and received are recognized, and they can also be monitored from where they are coming from to where they are going, such kind of things. What devices are receiving, what devices are sending those signals. So protocols normally are very, very key in networking and in any kind of communication. That is why there are different kinds of protocols, especially when you are dealing with the internet and networking. In networking, you discuss the internet protocol. The internet protocol is the one that governs how the access of internet. When you open websites, when you open emails, when you do things over the internet, there is a protocol that governs communication to happen to all. That is why even sometimes when there is a website that you have been blocked from opening, you will also see that you've been blocked and it will say service unavailable. What makes that kind of communication? It is that internet protocol that makes that possible. So it is a standard. A protocol is a standard that ensures that communication works in an agreeable way from sender to receiver. There is also hypertext transfer protocol. Hypertext transfer protocol is the standard for opening links. Hypertext are links. Those blue links that you normally open, they are called hypertext because they lead to some resources. You can click them and they lead you to some resources. So there is what we call the hypertext transfer protocol. That is why every time you open a website, it begins with HTTP or HTTPS. Okay, the hypertext transfer protocol is basically manages your as you navigate between one link and another. Click this link, click another link, and that is why you are able to whenever you are using the internet, you are leaving what we call digital footprints. You are leaving digital footprints. What are digital footprints? Digital footprints are basically the URLs that you have opened, the links that you click. Those are footprints. What you touched. It's like when you are walking from here to somewhere, and you are walking through sand or mud, you just you'll find out that you leave your footprints, right? So there are digital footprints, yeah. And an intelligent company can actually use your digital footprints to determine what you are normally interested in, what are the things that you normally do when you go over the internet. And that is even how companies are able to, that is even how or even Google itself. Let's just talk about Google. Google is able to know what you are normally interested in. So you are visiting a website randomly, but it pops up for you adverts for some certain kind of things that you could actually be interested in, right? You could actually be interested in. Why? Because as you navigate through the internet, opening this link, closing that, opening another, you are leaving digital footprints. So Google is intelligent, all right? Whatever the search engine, whether it's Bing or Google, it is intelligent. It's able to know. It's able to know the different kind of internet visitors and what they are interested in. So if there is a web things that there are adverts that they need to to give to different internet visitors, you find that you and I, when we visit the same website, if you visit a certain website and I visit another website, the ads you're going to get on that website can be different from the ads I'm going to get, because mine have been determined from my digital footprints. Okay, so it is these protocols that actually keep a record of what communication is going on. So there is HTTP for navigation from link to link. There is internet protocol for generally the whole internet experience. There is what we call the transfer control protocol, TCP, and that one manages things you send via email and such things. So protocols are basically standards or rules that manage how communication happens. All right. Uh, I'm going to discuss these two types of protocols. There are two types of protocols in transmission of data. There are two protocols generally, if and this is not about the internet itself, but generally protocols that govern communication, whether it's internet or just a local area network. Devices that are communicated to each other, like screen to screen, yeah, screen to computer, speaker to computer, using a data communication processor. Those kinds of communication where different devices are sending data signals. So there are different protocols that govern how communication happens when input and output devices are connected to a central computer. One of them is it's called the character-oriented protocol, and this one is called the bit-oriented protocol. The character-oriented protocol uses a standard called the American Standard, the ASCII. It includes this. Basically, this protocol is able to include uppercase and lowercase letters, numbers, and a variety of special symbols. And therefore, the characters that control the transmission, these characters are called communication control characters. So character-oriented protocols are protocols that govern communication where the following is allowed: uppercase and lowercase letters, numbers, and special symbols. And then the bit-oriented protocol. The bit-oriented protocol is basically, it doesn't use characters to manage communication, but it uses what? A bit string. A bit is basically a binary number which can either be 0 or 1. So a bit string, we are talking about as a combination of different bits or bytes. Yeah. And the difference between character oriented and bit oriented is that bit oriented is not CPU intensive. Bit oriented protocols are not CPU intensive. Why do I say that? Because the CPU of the computer interprets and executes instructions that are binary in nature, right? Machine language that are binary in nature. So bit oriented protocols, they already use bits. Okay, they already use a binary kind of mechanism. They use a binary mechanism to manage communication. So they are not processor intensive because they don't have to be done what? They don't have to be translated because they're already in byte form, they're already in machine language. But character-oriented protocol is a lot of translation that needs to happen. Now, character-oriented protocol, this is the protocol. It's the standard for communication if we are using multimedia devices. For instance, screens normally produce images, motion images, videos, uh, also characters themselves, the numbers, letters, special symbols, and such things. Okay, so character-oriented protocols they normally support multimedia devices, but bit-oriented protocol they normally support devices that are not multimedia in nature. For instance, we are talking about things like a computer connected to a printer, right? So that is not multimedia in nature. The communication happening is not multimedia in nature, right? It is not multimedia in nature. So it is in bit form. It is in bit form. So that is the that is the difference between character-oriented protocol and bit-oriented protocol. Character-oriented and bit-oriented protocol. Now, I want us to stop at that. I want us to stop at that so that in the next class we are going to discuss interrupts. What is an interrupt? Again, we've already discussed what is an interrupt. It's basically a signal of highest priority. But anyway, we are just going to come back and discuss it now as a subtopic in this topic of input-output organization. We'll continue discussing that interrupts, what is an interrupt, types of interrupts, and how to handle interrupts. We're going to come and discuss that in the next class and as we move on. So that is what we have for today. That is what we have for today. So is there any question? Any question? So see, if you guys have no questions, you have no questions. So if there be no questions, then we are going to stop it at that. Then in next week we are going to pick up from where we've left. We discuss interrupts, and you will be able to introduce chapter 3, memory organization. So let's call it a day. Let's call it a class. Have yourselves a good afternoon and keep yourselves safe.